In a world overflowing with data, extracting meaningful insights is paramount. Machine learning provides us with powerful tools to navigate this data deluge. And among these tools, clustering stands out as a cornerstone of unsupervised learning. Imagine having a massive collection of customer data, each data point representing an individual's preferences, purchase history, and demographics. Clustering allows us to unlock the hidden patterns within this data, segmenting customers into distinct groups with similar characteristics. Clustering algorithms empower us to make sense of unstructured data, uncovering natural groupings and revealing underlying structures. These groupings can then be leveraged for a multitude of applications, from personalized marketing campaigns to targeted product recommendations. By identifying similarities and differences within our data, clustering paves the way for more effective decision-making and deeper insights. Clustering is a machine learning technique that involves grouping data points into clusters based on their similarity. It falls under the umbrella of unsupervised learning, meaning that it operates without the guidance of pre-existing labels or categories. Instead of relying on explicit instructions, clustering algorithms learn from the inherent structure of the data itself, identifying patterns and relationships that might not be immediately apparent to the human eye. Imagine you have a basket of different fruits. You instinctively group them based on their features, and apples with apples, oranges with oranges, and so on. Clustering algorithms essentially perform the same task, but on a much larger and more complex scale. They analyze the features of data points, such as customer demographics or product attributes, and group them based on their proximity in the feature space. This process of grouping similar data points together forms the foundation of clustering analysis. K-means clustering is a widely used algorithm known for its simplicity and efficiency. It aims to partition a dataset into K distinct clusters, where K is a predetermined number specified by the user. The algorithm embarks on an iterative journey to find the optimal cluster assignments, constantly refining its solution until convergence is achieved. The journey begins with the selection of K initial cluster centroids, which are points that represent the centers of our initial clusters. These centroids are often chosen randomly, and their positions will evolve throughout the clustering process. Each data point in the dataset is then assigned to its nearest centroid, forming the initial clusters. Once all data points have been assigned, the centroids are recalculated based on the mean of all data points within their respective clusters. This process of assigning data points and updating centroids repeats iteratively until the centroids no longer shift significantly, indicating that the algorithm has converged to a stable solution. At this point, the K-means algorithm has partitioned the data into K clusters, with each data point belonging to the cluster whose centroid is closest to it. Section 4. Customer Segmentation, a real-world application of K-means. K-means clustering finds numerous applications in the real world, with customer segmentation being a prime example. Imagine a business seeking to understand its customer base better. By applying K-means to customer data, such as purchase history, demographics, and browsing behavior, the business can segment its customers into distinct groups. Each cluster will represent a group of customers with similar characteristics, allowing the business to tailor its marketing campaigns and product recommendations more effectively. For instance, one cluster might consist of high-value customers who make frequent purchases. This group could be targeted with exclusive promotions and loyalty programs. Another cluster might comprise price-sensitive customers who primarily purchase during sales. This group could be targeted with discounts and budget-friendly product offerings. By understanding the unique needs and behaviors of each customer segment, businesses can optimize their marketing strategies, enhance customer satisfaction, and ultimately drive revenue growth. Section 5. The elbow method. Finding the optimal number of clusters. One crucial aspect of K-means clustering is determining the optimal number of clusters, or K. Choosing an appropriate value for K is essential for obtaining meaningful and insightful clusters. Too few clusters might oversimplify the data, while too many could lead to overly granular and less interpretable results. The elbow method provides a visual and intuitive approach to finding the sweet spot for K. This method involves plotting the within-cluster sum of squares, or WCSS, against different values of k. The WCSS represents the sum of squared distances between each data point and its assigned centroid. As k increases, the WCSS generally decreases as data points are closer to their respective centroids. The elbow method plot typically resembles a bent arm with a distinct elbow point. This elbow point signifies the value of k where the decrease in WCSS begins to level off. Choosing k at the elbow point often provides a good balance between minimizing WCSS and avoiding unnecessary complexity. Section 6, Advantages and Limitations, a balanced perspective on k-means. K-means clustering offers several advantages that contribute to its popularity. Its simplicity and computational efficiency make it a suitable choice for handling large datasets. The algorithm's iterative nature allows it to refine its solution progressively, typically converging to a local optimum. Furthermore, k-means is relatively easy to implement and interpret, making it accessible to both beginners and experienced practitioners. However, k-means also has limitations that should be considered. One limitation is its sensitivity to the initial placement of centroids. Different initializations can lead to different final cluster assignments. Additionally, k-means assume spherical clusters, which may not be appropriate for data sets with complex shapes or varying densities. Moreover, k-means requires the user to specify the number of clusters, k, beforehand, which may not always be known in advance. Despite its limitations, k-means remains a valuable tool for exploratory data analysis and uncovering hidden patterns. By understanding its strengths and weaknesses, practitioners can leverage k-means effectively for a wide range of applications. Section 7, Conclusion, k-means, a powerful tool for data exploration. In the realm of machine learning, k-means clustering stands as a testament to the power of simplicity and iteration. Its ability to partition data into meaningful clusters based on similarity has made it an indispensable tool across various domains. From customer segmentation to image recognition, k-means continues to unlock valuable insights from data. As we navigate an increasingly data-driven world, understanding and harnessing the capabilities of algorithms like k-means becomes paramount. By embracing the principles of unsupervised learning, we empower ourselves to explore data, uncover hidden patterns, and make more informed decisions. K-means, with its intuitive approach and practical applications, will undoubtedly continue to play a pivotal role in shaping the future of data exploration.